All right. So when condensing approximately a year's worth of PhD research into 8 minutes, you have to be a bit selective. So to all of those people here who are not interested in deep learning, I'm very sorry. It's going to be a methodology talk. Um, I'm not going to talk too much about MALDI-TOF MS because let's be honest, who's really excited for MALDI-TOF MS? It's probably the most boring MS technology being talked about here. So I'm going to talk about transformers and I'm going to talk about pre-training. So having said that, I do have to introduce it a little bit. So MALDI-TOF MS, it's being used in clinical diagnostics. So imagine you're sick, you go to a hospital, they take a blood sample, a urine sample, whatever, you're infected. They grow it up a little bit, they put it into a MALDI-TOF mass spectrometer. Out comes a spectrum, and this spectrum can be used to identify what kind of infection you have. If you want to go a step further, you can also identify immediately the antimicrobial resistance profile of whatever infection you have. So one task, species identification, it's your standard run-of-the-mill multi-class classification task. Antimicrobial resistance prediction, you could also see it as multi-class classification, but then a biological step further. But you can also see it as like a recommendation task, like Netflix, recommend me the best drug for whatever this infection is. The problem with MALDI-TOF MS has been historically public labeled data, which makes it a little bit uninteresting for me, who's coming from a machine learning perspective, because I can't apply my overly complicated machine learning solutions. 2 years ago, people from Zurich published a large data set containing a lot of MALDI-TOF mass spectra, this data set allows me then to have some fun. And by having some fun, I mean apply transformers. So I think transformers are something that the mass spectral community should be kind of excited about. So I am going to motivate why you would consider transformers on mass spectral data in general. So if you want to go the deep learning route for mass spectral data, you have a couple of choices. The foremost I list on this slide. They all have their conceptual issues, according to me. Of course, I'm biased. Transformers, for me, they don't have those issues. So I'm going to let the slide speak for itself a bit here. So with MLPs, you need a fixed length feature vector, and that requires binning your spectrum, and that comes with a lot of arbitrary choices and also its issues. With CNNs, you kind of assume that peaks next to each other will be relevant for each other, which is not biologically the case. With RNNs, you then assume some kind of sequentiality, whereas a spectrum is not really a sequence, it's kind of a set. Transformers, you can kind of see them as like a jacked up graph neural network. So they will not assume a sequence. I know people think this because it's being foremostly used in natural language processing, but actually they're kind of a graph neural network. So they don't have this issue. So how would you go about applying transformer to mass spectral data in general? In language, take a sentence. It's correct. Each word in that sentence is characterized by two things: the word identity and its location in the sequence. With spectra, you have much of the same. Each peak is characterized by mass over charge, so its location, and then also an intensity. So you don't really need to make much modifications from the standard transformer networks if you want to apply transformers from language to spectral data. So I tried this on the tasks, bacterial species identification, and antimicrobial resistance prediction. And it turns out this didn't give me better results than the models I take issue with. So I wasn't happy. So I turned to pre-training. So pre-training or self-supervised learning can help alleviate that gap. And this is important for transformers especially because they're a very general class of models. So they can reach high capacity skill ceilings, essentially, but you need to throw a lot of data at them, which is where pre-training comes in. So the general rationale behind self-supervised learning is you take a model and you kind of try to design a task for which you don't need labels. So it used to be called unsupervised learning. Nowadays, people call it self-supervised learning. If you pre-train a task using such a design, you can call it, if you want to be really overhyped about your research, you can call it the foundational language model. It will get all of the citations, trust me. But if you use that model, then you can use it for your downstream transfer. Yeah, this is called transfer learning, essentially. You can use it for your downstream supervised learning tasks. The standard self-supervised learning technique to apply here would be masked language modeling. And people in metabolomics have already tried this out, and it works there. So I figure let's try it on MALDI-TOF data as well. It works, but I have some issues with it. So masked language modeling, long story short, you try to noise your data in a way. So for example, you take a spectrum and you mask out certain portions of your input space. So for example, you can mask out the intensity of certain peaks. So you say to your model, hey, I have this spectrum. I know I have some peaks here. Give me their intensity. You can pre-train your model this way. You can also do it the other way around. You can give your model a spectrum. You can mask out not the intensity, but the mass over charge. So you can say, hey, I have the spectrum. I have peaks this high. Where are they located on the mass over charge range? So some conceptual issues I have with this masked language modeling design is that mistakes can often be not really mistakes. For example, let's say you mask out the mass over charge range, and you say, I have a peak of this height. Well, any number of possible answers can be correct. For example, in this spectrum on the slide you see here, there's actually a lot of peaks that have the same height. So let's say you ask your model, I have a peak of this height. Where is it located? Multiple possible answers can be correct. And your model will penalize every answer but one, because your loss function will only give that one answer a zero loss. So another conceptual issue I have with this is that you have to introduce this masking token, which is not encountered during fine-tuning, only during pre-training. So actually there is a data distribution shift between pre-training and fine-tuning. So I set off to fix these issues, and I designed a new pre-training task, which is based on contrastive learning. The whole idea about contrastive learning is that you kind of distinguish what is real and what is fake, or what belongs and what doesn't belong with each other. So let's say you give your model two spectra in a batch, and you shuffle some peaks around. So you take some peaks of the one spectrum and you give them to the other spectrum, and you do the same vice versa. So now you have a new batch of spectra, and in each spectrum, some of those peaks are original peaks, and some of those peaks are introduced peaks from another spectrum, so fake peaks. Now you can ask your model, try to find the fake peaks, try to find the imposters. So this is essentially a binary classification task, and I call this peak shuffling discriminative language modeling. So this gives me better results in my downstream tasks, so bacterial species identification and antimicrobial resistance prediction. It gives me better results than masked language modeling. That's the end. I didn't give quantitative results in the interest of time, but you can find them in the preprint.
Thank you very much for a very entertaining talk. We have, okay, we can take one question if we have some. Go for it, Timo.
So can, for example, your transformer predict noise peaks after it learned actually the wrong ones from the shuffling process? Are they similar to noise peaks? And could it later also classify peaks in a real spectrum as noise, for example?
So this we tested out in the preprint. So exactly, during pre-training, we noise artificially the spectra, but during testing, you can test out, like, don't shuffle peaks, and then try to also try to predict what are the noise peaks, and it will actually consistently pick out peaks that otherwise would not appear if you kind of look at it globally. For example, I tested this out. Take all of the spectra that belongs to a certain species. You kind of assume in MALDI-TOF that those spectra will have peaks in the same location. And wherever that was not the case, it always said that it was a noise peak, whereas those were identified by the MALDI-TOF mass spectrometer, but the model set could pick it out as noise, and I assume it is noise.